Good evening, my dear students. My next lecture is on method of variation of parameters. So already in the previous lecture, we have learned about how to solve homogeneous linear differential equation. So I'm just talking about a linear differential equation. It is the most important part of mathematics, especially differential equation. So method of variation of parameters is another method to find out the particular integral. So again, I have to start from the linear equation of nth order. This is the well-known linear equation of nth order, where P1, P2, P and Q are constants or functions of x, but in our chapter, it is a constant coefficient. So P1, P2, Pn, etc. are constants. Q may be function of x, and therefore reduced equation Q should be 0, right? For reduced equation, we have to consider Q as 0. And let us consider a second order linear differential equation. That is d2y dx2 plus px dy dx plus qxy equal to rx. Now, let me state one theorem for you. And this theorem is very, very important. That will give you the method actually. And I will give you the proof of this method, proof of this theorem also. So, just start with the theorem. If y equal to phi 1x and phi 2x be two linearly independent solutions of the corresponding homogeneous equation of 1.2. So this is your homogeneous equation because Rx is a function of x, in which P, Q and R are continuous functions on subinterval I. These are all continuous functions in subinterval I. Okay. And a particular integral y equal to ypx on I of the non-homogeneous differential equation. So what is your non-homogeneous differential equation? If Rx equal to 0. If Rx equal to 0, that equation is called non-homogeneous. Otherwise, it is homogeneous, right? So, then a particular integral y equal to ypx on I of the non-homogeneous differential equation is given by this formula. Ypx equal to v1x phi 1x plus v2x phi 2x, where v1x is given by minus integration phi 2x rx by wx dx, and v2x is integration phi 1x rx by wx dx. Phi 1x, phi 2x are functions of x, rx and wx are functions of, where w is actually nothing but your Wronskian of phi 1 and phi 2. You have seen that your Wronskian is the determinant, right? Phi 1, phi 2, phi 1 dashed, phi 2 dashed. This determinant is called the Wronskian, and you have independent solution if this determinant is non-zero, right? So this Wronskian is W. So this is the formula for evaluating V1, V2. Let's come to the proof. Since phi 1x and phi 2x be two linearly independent solutions of the homogeneous differential equation Ly equal to 0, your differential equation can be written as linear operator. This can be written as Ly, right? L is a differential operator, where Ly is y double dashed, that is a double dashed or double prime is actually the derivative, second order derivative, first order derivative. So this is your Ly. Obviously, y equal to c1 phi 1x, c2 phi 2x is the general solution of it. Because it is said in the theorem that phi 1x and phi 2x are two linear independent solutions. Obviously, you know that, you have seen that superposition principle are followed by linear differential equations. So if phi 1x, phi 2x are linearly independent solutions, any linear combination of them will be the general solution of it, where c1, c2 are arbitrary constants. Now, by this method, we have to find two variable functions v1x and v2x such that this relation holds. This is your yp, particular integral, will be a pi of the non-homogeneous equation on I. Now differentiating this 1.4, this equation with respect to x successively twice. I am differentiating twice. So this is your first order derivative. This is your second order derivative. Now 1.5 and 1.6 substitute in the given equation. So if you substitute, you will have after calculation this type of form. This is your L phi 1 and L phi 2, and provided that L phi 1, L phi 2 is 0, because phi 1 is a solution of that equation, differential equation, and phi 2 is a solution of that differential equation. So it will be 0. So you will remain with these three terms inside the bracket. Okay. Now, since yp is a particular integral of 1.2, we have only one known condition. This is the known condition. Lyp is Rx. Because it is given, you have assumed that yp is a particular integral of 1.2. So it will satisfy the differential equation. So naturally you can write Lyp equal to Rx. Now, to determine two functions v1 and v2, we must need two linearly independent equations. So, but you have two unknown functions v1 and v2. Look at that initially. Let me go to the first step. Yeah, you see in the theorem, you have to find out v1x and v2x. These are the unknown functions you have introduced, and phi 1x, phi 2x are two linearly independent known solutions. So your unknowns are v1x and v2x. These are the unknowns. So you have to find out unknowns v1, v2. So you need two equations, independent equations, linearly independent equations, such that they satisfy this Lyp Rx. So one of the easiest way to obtain such pair of independent conditions satisfying this is to consider, you can consider from this equation. So if this is equal to 0 and this equal to Rx, then that equation is satisfied. So look at that, this equal to 0, number 1, and number 2, this equal to R. V1 prime, phi 1 prime, V2 prime, phi 2 prime equal to R. Then this equation is satisfied by this last. This is the simplified form. This equation will be satisfied that particular integral. So these are the easiest way to calculate. So these are the two. So what you will do, what is the next task for you? You are going for the solving these equations. So you will solve this and this for v1 prime and v2 prime. So if you solve, you can calculate the coefficient matrix, determinant of the coefficient matrix by the Wronskian. So if you solve, your v1 prime will be like this. This is your v1 prime and v2 prime. And if you integrate, there is some typographical error. Dx should not be there. This is your v1 prime, v1, v2 prime. But if you integrate, the integration dx will come. Integrating the above result, we obtain the final result of the theorem. Okay? So that is how you can calculate the unknowns v1, v2. This is the result. If you integrate, you will get the theorem. This is the theorem. This is the result by integration, right? This is the theorem. So this is the very simple proof of the theorem. And why I am doing this? That questions are answered. So some remark. Keeping in view of the general solution C1 phi 1x, C2 phi 2x of the homogeneous differential equation, this is your homogeneous because Rx is 0. It is always possible to find a PI of the form this. It is always possible. This is the remark 1 of the non-homogeneous differential equation. You can always get the particular integral of the form this. And remark 2, the functions v1x and v2x are actually obtained by indefinite integrals v1x minus integral over x phi 2 xi r xi by omega w xi d xi and v2x. Hence, a particular integral y equal to ypx for all x belongs to I can also be expressed as, you can substitute replacing v1 and v2 by this integration. That is, this is valid for all x belongs to the I, for all x, whatever be your x. So this will be in this form, yp. Yp will take this form. This is the form of yp. Okay? And for any particular x naught, you can calculate this integration. And remark 2, it's a historical note. The procedure by which we obtain here a particular solution ypx is known as the method of variation of parameters. It was first used by Johann Bernoulli in 1697, that is at the end of the 17th century, to solve linear equation of first order, and then by Lagrange in the 18th century, 1774, to solve linear equations of the second order. So that was the historical note behind these calculations. Now let's solve some problems. So our first problem is d2y dx to a squared y equal to cosec ax. Already we solved this type of problem in the previous chapter, that is linear equation with constant coefficient, by using particular integral technique. But here you know that the auxiliary equation is m square plus a square equal to 0. So you have the complementary function, so complex roots of the differential equation. So your complementary function will be like this. This is very simple to calculate. C1, C2 are arbitrary constants. The Wronskian of the two functions are phi 1x equal to, so sin ax and cos ax are two independent solutions. Because the Wronskian is not equal to 0, you can calculate the Wronskian phi 1x, phi 2x, phi 1 dash, that is the prime, that is the derivative, and phi 2 prime. Therefore, phi 1 prime, phi 2 prime are linearly independent. Okay, so you can calculate the Wronskian. Hence, by the method of variation of parameters, a particular integral is given by the function ypx equal to v1x phi 1x plus v2x phi 2x. This is the formula. Already we have explained in the theorem, proving is there. So you can calculate v1x by this formula. Very simple. Or you can do a lengthy process by calculating the technique which I have described in the proving. You can take the help of the proof. You can calculate everything like this. You can use this technique. You can calculate like this. You can check and you can calculate by, and lastly you can solve like this. Or in a very short method, you can use these results v1x v2x by integration. You can check, this is the integration, this is your v1x and this is your v2x. And pi of the given OD is given by this one, because C1 v1x phi 1x and v2x phi 2x. So v1 is minus x by a and v2 is log mod sin x by a square sin x. And the complete solution is given by Ca plus pi. This is your complete solution, where C1, C2 are arbitrary constants. This is how you can use your variation of parameter method to find out the particular integral. Next problem, tan ax. It's the same problem, same type of problem. You can try this problem, but I have done up to linearly independent. You can take help of the previous problem to calculate the v1x, v2x, Wronskian and all that. Lastly, I will show you another problem. This is the last problem. So this is the auxiliary equation m square plus twice m plus 1. So this is your complementary function c1 e to the power minus x, c2x e to the power minus x. So your phi 1x is e to the power minus x and phi 2x is x e to the power minus x. So we have to check whether phi 1 and phi 2 are linearly independent or not. So you have to check the Wronskian. If Wronskian is not equal to 0, they are linearly independent. Otherwise, they are linearly dependent. So we check that the result of the Wronskian is e to the power minus 2x. So phi 1x, phi 2x are linearly independent. Now you write the particular integral in this form: ypx equal to v1x phi 1x, v2x phi 2x, where phi 1 and phi 2 are linearly independent solutions, and v1x can be calculated by these results. These are the results stated by the theorem. So v1x is minus phi 2 rx by wx. So what is your rx? Rx you see e to the power minus x by x squared, and wx, that is the Wronskian, is e to the power minus x, and phi 2 is x e to the power minus x, right? This is your phi 2. This part is your phi 2. So if you simplify, you have, after integration, you have minus log x. Similarly, you can calculate v2 by substituting phi 1, rx and wx remain same. So it will be minus 1 by x. So this is your yp, v1x phi 1x and v2x phi 2x. If you substitute, you have yp as this form. And finally, you have the general solution in this form: Ca plus pi. C1 e to the power minus x, C2 e to the x e to the power minus s, and the pi, particular integral. So you see how easy to calculate by the variation of parameter. It is a very easy method, but you can do the long process also by the proving of the theorem. You can use the proof of the theorem to calculate the long process, take the long process to calculate the particular integral. Okay, all of you. So in this video, you have learned about the calculation of the linear differential equation with constant coefficient, or maybe there are some functions of x by variation of parameters. So next, I will teach you method of undetermined coefficient for finding the particular integral. Thank you, all of you.